and then now I'm going to come and I'm going to do my high mag plane on this surface. So I'm going to do a plane, more inputs, focus point. Let's call it a F-scan point. A focus point right here. I'm going to do the same thing, right click, rotate 90 degrees, 3 copies, right click, remeasure. Less work for me, let the computer do the work for us. So now I'm going to reset my origin of X and Y to my circle, set my origin of Z to my plane, and now I'm good to go. I'm going to call this datum A and B. All right, so now I look at my blueprint, and my blueprint says the next level down that we need to measure a height is down about, not about, my blueprint says 0.472. So I come over a little bit to the side of my plane, so we're in focus. This is our 0 point now. Now I can move over, right click, move to absolute, down in Z, 472, and boom, now we're at the surface. I'm going to do plane, focus point, right click, rotate, 93. So I got that plane. So I'll do that again. I come over here, my blueprint says the next surface down. I right click, move to, I just look at my blueprint. It says, okay, the next surface down is 796. Boom, I'm right there. I do another plane. I do a focus point. I right click that focus point, rotate, 93. I got the other plane. And if I wanted to, the overall height of this part is 0.887 on my blueprint. So I'm going to come down, and that is the glass. So if I wanted to, I could put a little dry erase marker right here, or if your stage is dirty like mine, I can do a focus point off the glass, and then I'll be able to do a height from all of that. So we wrote that program pretty quick using the right click, move to absolute. Now let me explain all of that, what I did. I wanted to run through that really fast just to show you the speed of using it and how that helps you out. But when we right click and move to, the move absolute is off of your datum structure or your system. Since we set the origin of Z to that top plane, that means that top plane is now our 0 in our DRO. That's where the coordinate system is. So when we right click and move absolute, we're moving in relation to our system that we're in. So since the top plane is datum A, and I said that my 0 and my blueprint represents the same thing, I can punch in those numbers. You just got to be real careful, because if you're in the wrong system and you say move down negative 0.88 and your part is only, your part is say, 3 inches tall, you could crash into it. So just be real careful with that, using the move absolute. So you notice that I didn't right click and remeasure these. If I was just writing my program and just moving through the motions, I was just going to do that to get my program done. And so now I can do a distance from my top plane to this guy. And I'll go ahead and rename this dimension 1. I'm going to hit F3, or you can right click tolerances. And my Z height is supposed to be 0.472 plus or minus 5. And I'm going to go ahead and export that. My Z height. And I'm going to do a distance from my top plane datum A down to my bottom. And that is going to be dimension number 2. Open up my tolerances. This is supposed to be 796 plus or minus 5. I'm going to hit F4 and I'm going to export that Z distance. And then my last one, I'm going to do a distance from datum A down to my one focus point that is on the glass. Now, here's the thing, is I will always try my best to do a distance in the Z axis from plane to plane. But if I can't, or because I'm on the glass and I just want to do 1 point, that's almost like using an indicator that we're dropping down to do an overall height. I'll at least do a plane to a point. I really don't like doing point to point. The z-axis is going to be accurate, but there could be some error in that XY distance that we'll see that it includes. So I don't like to do that. So I'll always try my best to do plane to plane. If I can't do plane to plane, I'll at least do a plane to a point. But worst case, if I have no option of plane to plane, we can do point to point and then just look at the z-axis here. I'm going to go ahead and name that one number 03. Tolerance that's supposed to be 887 plus or minus 5. That guy's out. And then export that z distance. All right, so let's go ahead and let's run this guy. So I'm going to hit run. I go find my part. Here's a little trick too, that if you are doing semi-automated programs, so you're taking the parts on and off and you're just plopping it down on the stage, what you could do is before you start your program, you can right click on that arc and say move here. It'll move to that z-axis that it wants to be at, and it'll be at the location that you programmed. So before you even run your program, if you come to your first feature and say move here, it'll move to the z height that you programmed it at and the location. So now I can move my part into location and I'm right here, good to go. So I'm going to hit run. My tool's already selected for me. So I hit arc, continue, hit my focus point, hit continue, and now we're off to the races. Doing our datum A right here. Now it drops down to the next feature. And we're good to go. We got all of our results. Boom, done. All right, now you've all probably been so anxious to hear about and not scared at all is let's talk about if we have a blueprint. Yes, this is a simple blueprint that I drew on paint this morning just to show if you ever see multiple GD&T symbols on top of each other, there is a rhyme and reason the engineer or whoever drew this wants that. So this is where you take notes because I don't have a lot of slides for this for you today, but we go over a lot of this in the two-day GD&T fundamentals class that we have. Profile controls location, orientation, and form. So that profile symbol, you know, don't write me nasty emails. I love profile. It's a great tolerance to place on features because it controls a lot. It's very powerful. Now, what scares a lot of people about profile is how do we measure it? That could be difficult. That's why you have people like me, people like ATI. We can assist you with that. We can help you understand, okay, what is it? What's it kind of control? And we can, you know, give you suggestions on how to measure it. But profile controls location, orientation, and form. So this, if we erased parallelism and flatness and we just had profile, it would already be controlling parallelism and flatness. But in this case, profile is like our blue guard bands right here. This 0.6 guard band is a 0.6 guard band. We're talking millimeters. If you're a 0.6 profile on inches, you can make the part however you want. But if we're talking millimeters, this blue guard band that you see right here is 0.6. Where does that guard band get placed? Well, it's in relation to A, so you'll always, or you should, have a basic dimension that brings you from the surface that they want controlled to the datum that it's controlled from. So let's say that this basic dimension is 25 millimeters. That means that this blue profile guard band is being placed perfectly at 25 millimeters from datum A. Now, we haven't talked about fixturing, we haven't talked about all this different stuff, but this is just, let's say, 30,000 feet view of what this is controlling. So profile is controlling location. So that means that this surface can grow 0.3 and still be in tolerance, or this surface can shrink 0.3 and still be in tolerance, because perfectly we're at 24 inches or 24 inches, 25 millimeters. And so we could be 25.3 or we can be 24.7 in height. So this is controlling location, which in this case, the location is a height of it. Also, this surface can be parallel within 0.6. So this could be angled up from bottom left to top right. And as long as it fits within that blue guard band, we're still within our parallelism that's within our profile guard band. We're still within tolerance. Now it also controls form. Again, profile controls location, orientation, and form. So this 0.6 is also allowing us to be 0.6 within flatness. So if we measured this and we had, let's say, negative 0.2 on our indicator, or a microview, a point over here, and then we had positive 0.3 over here, that means we have a total range of -2, +3. So our flatness would be 0.5, because you add those two together, that total range, to get our flatness reading. And then profile would be the worst case times 2. So 0.3 is the worst case, times it by 2, we get 0.6. So we're technically still within our limits. We're right there at the limit, but we would be able to still pass this part. So now if we have a call out like this on our blueprint, that means that the engineer cares about location. So we're going to say, hey, this part can grow or shrink 0.6 or 0.3 from our basic dimension, whatever it is. But now we want to control parallelism a little bit more, because profile, if we have a profile tolerance of 0.6, that means we could also have a parallelism and a flatness tolerance of 0.6. So we actually want to control location a little less than we want to control parallelism. So parallelism is our orange guard band right here, saying, hey, we want to make sure that we can be anywhere height-wise in this blue guard band. Oh, let's go back. We can be anywhere height-wise in our blue guard band, but we have to be parallel within our orange guard band. Orientation, which is your parallelism, perpendicularity, and angularity, those three aren't location-based. Wherever we measure that surface, it could be 30 millimeters high, it could be 2 millimeters high. As long as that surface is 0 degrees from datum A, measured with a decimal place with an indicator, you can be parallel. So size doesn't matter, height doesn't matter with parallelism. So the engineer wants to control that a little bit more. And also, we care about location a little less than our orientation, but we really, really care about our flatness. So we can put another flatness call out onto it of 0.1. Because flatness, if I took this, think about the table that you're sitting at. That table's flat. If you flip that table over right now, that table's still flat, no matter where it is in the room. So orientation and location don't matter to flatness onto that. So we put that in saying, hey, we want to have a location that's a little open tolerance. Parallelism is a little tighter. We want to make sure that we're 0 degrees as much as possible from datum A, but we really, really want to make sure that we're flat. Awesome. That makes sense, right? Hopefully it'll make all sense to you guys. How do we measure it? Now I'm going to come over to InSpec. I'm going to open up this program here. Hopefully my program didn't move. I'm going to hit run. Moved a little bit, so I just need to adjust my tools. We're going to let this program run here because I got two planes here, so top and bottom, that we want to measure. So let's think about that. If I have this plane right here and I have this plane right here, this is the same. Let's think about this as the same blueprint that we have. We have this plane right here and this plane right here. We want this to be datum A, and then we want to check profile to it, and we also want to check parallelism and flatness. All right, so we come down to these planes. This top plane is datum A. We want to have this controlled as datum A. So little trick is you could right click insert here. Wherever you right click insert here, it's going to start writing above that. So I'm going to say I want my origin of X and Y to be these diameters here. So I want my origin of X and Y to be circle 2. I want my origin of Z to be my datum A, and I want my skew to be these two datums. All right, so now I got my system all set up. If you ever insert a system within your program, if I click on this plane, even though it's underneath system 30, it's still looking at system 6. So you have to right click, set system to the correct system. So now I need to tolerance this profile. I need to tolerance as many basic dimensions as my blueprint tells me before I tolerance my profile over here. So if I come here, I have that Z height. That Z height is supposed to be, let's say, 032. That's what my blueprint says. Basic dimensions don't get tolerance. We just say what the nominal, what the perfect location is. So now MicroView knows where to place that perfect profile guard band on that surface. So then we come over to the profile tab. It'll pull those basic dimensions into our profile tab. So here we have a 5 thou tolerance guard band. That was our blue guard band here. It's a little larger. So that means that we can grow 2.5 thou or drop 2.5 thou. And then we also have that parallelism call out. This parallelism call out, we need to tell it what feature we want it to look at. Plane 28 is datum A, so we want it to look at datum A. I should have renamed it for ease of use, because if I renamed it, this would make sense. And this is supposed to be a 3 thou guard band, because we want parallelism controlled a little tighter than the profile. So parallelism controlled a little tighter than profile. Then we can come down to our flatness tab, and this one is controlled at 1 thou, and we're going to be out of tolerance. So you can apply different tolerances to your different features all within the same tolerance band. And if we look at this, there's our profile, there's our parallelism, and there's our flatness, and we got all of our readings right here, good to go. If a lot of that made sense, awesome. If you have any more questions on that, feel free to shoot me an email. We can follow up and talk more about this. If you've never seen GD&T stacked on top of each other, you probably will on Monday morning now. You're welcome. But GD&T might not be used a lot in your shop, but it's coming. The more and more these standards move on and get revised, we're moving more towards less plus minus tolerancing and more GD&T tolerancing on these features to really control our manufacturing process and our qualification process. To respect your time, we'll wrap up here. I'll save threads for the next time. There's some thread tricks that I want to show you measuring with the MicroView. But again, remember, go to our YouTube channel for any previous webinars. This webinar is being recorded. I'll throw it up on the YouTube channel when it's available. Remember our metrology services. If you have any PPAPs you want to send to us, reverse engineering, need custom fixturing for maybe profile or your microview, and we have tons of engineering solutions that we can help you with. Go ahead and scan this QR code. It'll bring you to our events page on our website. You can check out when the next classes are, or if you want to contact us for on-site training, feel free to email training@atiquality.com. We can set up on-site training at your facility or check when our training team is coming to a city near you in the Midwest. But that's all I got for you today. I'll leave that QR code up for you. I'll be sticking around here for a little while. If there is any questions you have, feel free to pop in to the chat and say, hey, can you explain that again? Or feel free to shoot me an email. I appreciate all your guys' time. Be safe this weekend if you're in the Midwest. That snowstorm's hitting here right now. But yeah, I appreciate you guys. Visit our website. Let us know if there's any training courses we could schedule with you. And I appreciate all you guys. Thank you. Have a great weekend. Hey, Maggie. Yeah, I sure can do that for you. So I will go back to that part and make sure that that's what you're talking about. So rotating the F-scan arcs around, another feature. I'm going to zoom out here, go back and find that part. If I can find the part. There we go. Were you talking about where I was able to, I measured one arc here on the side and then I rotated it 90 degrees and it did the work for me? Is that what you were talking about? So if we have here, if we ever use the rotate feature, if we ever want to rotate anything around anything, we need to rotate about a system. So our system needs to be the center of the part because we're going to rotate around that system. So what I did here is I kind of cheated where I did a diameter and I did a small F-scan arc right here to create a diameter. Or what I could have done, which now I look at this part more, is I could have set my origin to the center of this. It should be the same center, but we're all good there. So I'm going to set my origin to the center of that circle. So now I have something to rotate about because the center of this arc that I made that created this diameter is this center point right here. So now if I click circle again and I do this arc, I can come down here in my inputs. So I have one circle made up of this arc. So I want to rotate this arc. I don't want to rotate this circle. I come here, I right click on that arc and I go to rotate. And I say, I want an arc every 90 degrees. So I have one arc here And if I go 90, 90, 90, I need 3 copies of this arc. So I click OK, and then I can right click on that circle and remeasure it. And it places an arc, a copy of that arc every 90 degrees. And now they're not copies anymore. They're individual inputs that create up my one circle right here. Is that what you were asking there? Did that answer your question? And if we really wanted to, we could, get even more crazy that if I said, I want to circle this little F-scan arc and I want to rotate this every 22.5 degrees, that would be 15 copies because it would take 16 total arcs to get back to 360. Click OK, right click on the circle, remeasure. We're able to measure that there. Hopefully that answered your question. Going through that again, and remember, this will be on YouTube, if not this afternoon by Monday. And you'll be able to review it there too. See a few other friends still sticking on here. You guys got any questions for me? You want me to go over? I see Lisa. It's probably too cold for you to be watching the webinar down by the river by your shop over there at the picnic table. But got any questions, Maggie? Anything else? Hopefully that answered it. Oscar, Reed. See Chris, how you doing? If not, I'll probably be closing this down in about 5 minutes, 2 minutes. If I don't hear anything from you guys, appreciate it. Thank you guys. I should have scrolled down on my chat. It was stuck up way up in there. It looked like it was still stuck on the 90 degrees, but yeah, covering multiple lighting sources. I could take a couple seconds with that. One of my biggest things when I'm looking at different lighting sources for certain features is I start full surface light or whatever it is, and then I either add or subtract from there to really cue in to what I'm looking lighting wise. I got this blue part over here actually that might be good. I don't have an example off the top of my head, but I know this is kind of a difficult feature over here to look at. That's really interesting. The rotate caused that. So right here, I have my full surface light on, usually blind holes. So I can probably find a blind hole for you. But since I'm right here, I'll use this example real quick. Full surface light. If my edge looks great, I'm going to use full surface light. That's where my mind goes is, all right, full surface light, this edge looks good. I'm going to stick here. I'm going to be fine with it. Now, this edge gets a little weird. We have a lot of different, gray values going on, shadows. So this is where I start. Usually you'll see me go from full surface light to octants and see what it looks like from different edges. So if I bump this up a little bit, now we eliminated a lot of that shadow over there. So that's good to go. I just always like to check to see what the other side of the octants look, because you might be surprised. My first initial thought was go from this side, and it's working out for us. But sometimes you might be surprised that if you go the opposite side of what you're looking at, you might have a better lighting source. But in this case, nope. So we're going to go back to this side. It takes a couple seconds to switch lighting. Now, if this is good, which it kind of is, I'm kind of happy with that line for that edge. Yeah, this is a section part, so I actually wouldn't be measuring this. But now if this was still too much light, then I go down to segments and I'll click and drag around my outer ring lights just coming from this direction to measure that feature. So I start here. If this is good, awesome. If not, I start subtracting lights. So that might be good. So I subtracted these 5 octants. And now really, if we want to tune in or really like, you know, fine tune our lighting, I can even subtract some of the ring lights from my octants and get a really nice crisp edge right there. Now, usually talking blind holes. Let's see if I got a blind hole over here. Turn on surface light so I can find the part. Couple things that you need to be careful with blind holes is, let's see, do I still got paint up? So with blind holes, if we have this surface, actually pretty straight lines. Oh, there you go. Now it's not straight. You got to be careful where you want to take the measurement. If we're going to take the measurement here, that could be pretty easy because we use surface light. Maybe we use ring lights. So I'll use ring lights to show how to get the best lighting for right here. But depending on how this part is made, if it's made and it's like barreled a little bit, somehow our tooling, whatever made that happen, we don't get to see this diameter because our camera can't see that surface. Now, if we want, you know, if we have, that's a dramatic draft on there, or, you know, like a draft angle, that's nice because then we can see what our smallest diameter is down at the bottom because nothing's blocking our view. So that's a little tricky. Where do we want to take the measurement? And using those different Z heights that I was telling you about, where if we know how far that blind hole is supposed to go down, you can right click, move down that blind hole height, and you should be able to see that the bottom of it. Here's another thing too, while it's on my mind, is if we have this blind hole, depending on your manufacturing process, I know this won't be for every instance, you'll probably have a tooling mark at the bottom. And we want to measure from here to here. We don't want to measure this depth on here. So height-wise, we're measuring here, and that's the distance that we're probably going to want right there. We could use a caliper, and if we use a caliper, I always make sure that, erase some of this, that when I use my caliper, I make sure that little notch at the bottom of my depth rod is away from the sidewall because my caliper will hit at that point right there. So just think about that. So here, if I wanted to get the top of my diameter, looking at switching over to ring lights, see how it darkens the inside of my hole right here? So I'm really getting that top diameter really well. Instead of using this, now we can start seeing some of the bottom that we might not want to see. So if we want the top diameter, I switch to the outer ring light so I can see where that diameter actually starts. If your microview only has 2 ring lights, you can upgrade your microview to have 5 ring lights. You can just switch out the your standard ring light for a macro ring light. It's not terribly high priced at all. It's a great option that you can switch out. So now my outer ring light is farther away from where my camera is, so it's not shining harsh light down into there. Now I want to see if we want to get to the bottom of this blind hole. I hit auto lights and I bump up my lights a little bit. We can come down and see, you can see that tooling mark. So here's a good example. I can see this kind of crisp edge right here, but then it goes away over here because this part over here on the right side is probably leaning more to the right on my part. So it's blocking where I need to measure over here. Let's look at the difference between full surface light and ring light. So I'm just going to use a center ring light. I'm going to bump my lights up a little bit. Pretty much the same. We could also, if we know we're casting a lot of shadow over here, maybe we could have lights just coming from this direction. So all I did was switch the segments, my inner ring light just from that direction so I can get a crisper edge going on right here. Sometimes axial light helps, but it might get cloudy. See how cloudy